very good. That I don't.
So what is in Punjabi?
That I don't know.
In Turkish? Neither.
Yeah, I know, huh?
But neither.
Good either. That's quite difficult. Okay, so where? Tiki or that is the prediction.
Sindhi? Anyone in
Sindhi, huh?
Subha
Subha. Okay. Balochini. These are beautiful, beautiful words. These are beautiful words, and with that, I'd like to thank you for meeting me. When I was coming, my teacher, Dr. Tharula, walked into my office, and there was no way that I could say anything to him except to sit beside him. Wait for him to go. Okay, so Bismillah ar-Rahman ar-Rahim, and I just have this weird feeling that this 10, 15, 1 hour, even less lectures are not really sufficient. And NMR requires much more time. So for that, I think we will have some informal sessions. We'll sit together in very relaxed, setup and ask questions and try to answer them. Let's make it happen. Let's have this NMR cracked, have this spine broken and try to understand NMR to the core. Let's do it once for all. And so, this very, very exciting subject for good, inshallah. And so, we were discussing, I don't know where somebody. Why can't go back? Okay, so let's see this very, very interesting diagram, and that is called block vector diagram. Somebody long time ago realized that understanding NMR theory is not possible by just definitions. And the better version of defining NMR, especially modern NMR spectroscopy, is to use vectors. And that is called block vector diagram. And Flex Block was the first one. He was among the pioneer of NMR, but he was also the one who said NMR can be understood to a greater extent, not to all, by using vectors. Okay, and he was right, because these small, tiny nucleus, collectively nuclei, are actually magnets, and magnets have magnitude and a direction. Right, magnetic power has a magnitude and a direction vectors. And we all know that Boltzmann said that for spin-off nuclei, plus half, minus half, whole population, both energy states are equally populated, nearly, except a minor difference, and that is called Boltzmann distribution. And if you cancel them all, because they have opposite direction and the same magnitude, you leave with only the difference. And that difference is called net magnetization difference or Boltzmann distribution. And that makes life so easy for us. It makes life more easy because now we are dealing with magnetization vector which represent the difference in population. I wish to remind you that difference in population is dependent on V naught, okay, gyromagnetic ratio, natural abundance, and you keep doing it. So this M naught is called bulk magnetization vector. Bulk because it represents several vectors. And all kindly remember that this is an artificial construct because these magnetization vectors are precessing. But since the difference and they have the same kind of a direction, so you just put them together. Remember in vector, I'm sure that you remember your basic physics, like vectors can be combined together into bulk vector. So this represents a bulk magnetization vector. And now you can play with it. And if you know how to play with it, then you know NMR spectroscopy to the core. And this is what Richard Ernst played with it. And he said, why don't we just excite them together by giving a pulse? Okay, burst of radio frequency, which represents the entire window of all spin of the interest. Okay, radio frequency of the entire window. For instance, in ethanol, these are three different types of protons, and they have their own Lambda frequency, and the radio frequency has to be broad enough to bring all three of them together at the same time. And then it was so exciting. And he also mentioned right-hand thumb rule, not the left-hand thumb rule. Right-hand thumb rule. Okay. And right-hand thumb rule was that if you give radio frequency pulse perpendicular to the direction of M naught and also magnetic field from here, this is called B1. So the terminology used is called B1 because remember radio frequency is also magnetic. All electromagnetic radiation have oscillatory magnetic field. So they are wave. There is a magnetic field and there is electric field. So they all are magnetic, remember? And they also have photons flowing through. So they have a particle and they have a wave function, basically. So if you give radio frequency pulse B naught and you excite them together at the same time, pulse, and instead of recording the absorption, you record relaxation. Okay. So first, let me ask you, and if I say B1, radio frequency oscillation is from this side. This is your thumb. Everyone, right hand up. I'm so happy that you all know right hand. Because sometimes it's not so easy. I know some people who, they still struggle right or left. Okay, right hand. Okay. And then right hand, this is the direction of radio frequency pulse. B1. Okay. This is your M naught. M naught. And this is clockwise direction. Can you move your right hand anti-clockwise? Not really, not too much. I can't do it. If you can do it, you're acrobat. Right? So it is right hand thumb rule. So you curl like this. Okay, so if M naught is this one, you know exactly where your magnetic vector will go. Okay, take the easiest one. 180 pulse. minus Z. So easy, right? Okay, 90x pulse. When I say 90x, it means that I have given a pulse long enough to bring magnetization to 90 degrees. Where it will go? From X. Where? Imagine this 3 dimension. Or make this minus Y or Y. Right. Who can explain that? Amna. Come. Sudhar is a good teacher, right? Okay. This is X. This is not minus. This is minus X.
Like this?
No, X. The pulse is from 90x. When I say 90x, no. 90x. I will go to minus x also. 90x. It means your finger, it's not finger, it's thumb. Your thumb is towards the direction of x and 90. So from longitudinal to transfer. You know the term called torque? You know physics torque? So this is turning, you're turning. It's called torque. You're creating a torque condition. And that torque condition, why are you creating a torque condition? Because you make your life a bit more difficult. Because I don't want to oversimplify that. When you bring B0, B1, you're actually creating another magnetic field. And if you continue B0, B1, this would move like this. Right? But you're not doing it. You just turn on and turn off. 90x. Where it will go? Minus Y. Why?
Like this, yeah?
How can we throw a minus Y?
Plus.
Plus Y. So, division. I wish I can make a 3-dimensional. You don't understand, don't worry about that, you understand. Your finger, your thumb on X and your fingers on Y, on Z, right? When you rotate, where it will go? Y. Okay, now I'm going to use a here and give minus 90 minus X first. Minus Y. Okay, Aruna. 90 Y plus.
91.
Minus X.
Minus 8.
90 minus X plus. Sorry, I asked you already. Minus 90Y. That is difficult. Going behind is difficult. Yes. Yeah. Where it will go. Yes, sir. Please. This is an exercise in the body.
I'm not talking about that.
No,
In the previous slide,
Go ahead.
in the beginning,
This is not your right side. This is right? This is. No, what are you doing? Your hand, your fingers are 90. this is okay, and clockwise, turn clockwise. Just continue. Clockwise.
My question, sir.
Okay, come and see. Ask him first. I'll ask you a question. Can you have 90? Can you have 45 pulse?
Yes, sir.
180 pulse? 270 pulse? 360 pulse? Okay, very difficult question. If you give 360 pulse, where it will go?
Most correct. Comes pregnant.
Third way. 180 pulse. It doesn't matter from where you give the pulse that you put up. It's only when you try to break them on XY plane that you need to use. Yes, your question.
The previous slides, you explained about the gravity frequency of this pulse for three current in the pure and magnetic field. Now you
Perpendicular. So this is a perpendicular. Magnetic. This is the M naught, right?
Pure pulse from inside.
Yeah.
Okay, how it all these angles are absolute.
Yeah. This is your magnetic field M naught, and this is perpendicular.
How it is like this direction?
Yeah, because it's absorbing energy.
Yeah.
So
Or like when there is excitation or
excitation. When you absorb the
okay. Or
right now we're talking about excitation.
exactly. Now, since it's magnetic field, your nucleus is here.
Forget magnetic field. I want you to forget magnetic field. If you do not really forget magnetic field, you'll not be able to understand. We are talking about now, magnetic field is always present. Talking about the M naught, net magnetization vector of your sample. Okay.
And your running frequency from the every
Pulse
and pulse.
as a pulse.
Okay. What now we are talking about 90 or 100.
Right, because now you need to rotate this magnetization vector to various directions. Okay. This is the NMR spectroscopy. The modern NMR spectroscopy is not giving radio frequency and absorbing it. The modern NMR spectroscopy is to bring this magnetization vector in different places and to record them. And you will.
This direction is you mean about the position of this nucleus or what?
Yeah, it's magnetic vectors.
I mean, we have nucleus here in the alpha state.
Which nucleus? Okay, so proton.
Yeah, they are in the lower state. Some of them in lower state, some of them in the high state. No, now okay. After
Higher state in NMR is not up.
Making how the story itself.
Okay, so in NMR, higher energy state is not up. It's down. Because magnetic field is up. And anything which is alike in the magnetic field is on low energy state. Okay. Anything which is close to the magnetic field is higher energy state. Okay? So both energy states are nearly equally populated, except that low energy state has slight excess of magnetization. And that is called Boltzmann distribution excess. Distribution in two populations, there is an excess and discovered by Boltzmann. Okay, this excess in population is represented by M naught. Okay, because these are a few vectors which are in the same direction. So you put them together, they have magnitude and directions. Now, this is your a population of interest, nothing else. Because the population difference is the one which gives you signal. Remember, the difference in population is your signal. The more difference, better signal. And that is the reason I told you that population difference is dependent on various factors. Now this M0, life is so easy if you just absorb them. It's not modern NMR spectroscopy, because if this was the case, except proton NMR, nothing would have been developed. Nothing would have been developed. No COSY, no Z, TOXY, HMQC, HMBC. No experiments were possible if this was just like giving radio frequency and recording absorption. No excitation, no excitement in life. Okay? And I'm trying to make your life excited, happy. But you don't look happy here. Sheikh, I need to spend 2-3 days with you. I will take you with you. You need more time? Okay. Problem is that we have the same gender. No problem. Okay, so what I was saying, I forgot. 90. So, I suggested you kindly make this 3-dimensional partition and try to understand this concept, because after some time, I will not really tell you about right-hand thumb rules. I will just tell you 90 X-bars. Okay. And I will also tell you minus 40 pounds or something like that. I'll just tell you about this. The vocabulary will be not showing you this. The vocabulary would be just to tell you 90 X-bars or minus 80 pulse, minus 80 Y pulse over. So you should be able to have this mental gymnastic in your mind. I'll tell you the utility of this. You have, for instance, you have ethanol. Okay. And you have 3 elements: carbon, hydrogen, oxygen. Okay. And you want to record only proton. How would you record it? Your pulse has to be in the frequency which is matched with proton. But protons are coupled with carbon-13, right? And you don't want carbon-13, you don't want to see carbon-13 coupling. You don't want to see carbon-13 coupling. You don't want your proton splitted by carbon-13. Now, with this one example, you would understand the utility of it. So we will bring 2 radio frequency oscillator. It's very difficult, but very exciting. 2 radio frequency oscillator. You bring 1 radio frequency oscillator, which gives 90 XH pulse. Proton comes on XY plane. And then you bring another radio frequency oscillator, which gives infinitely large carbon-13 pulse. You turn on the radio frequency on carbon-13. You turn on the radio frequency on carbon-13, and carbon-13 will be moving along Y, X minus Z minus X minus Z minus X, like this, like a fan, right? And when carbon-13 is totally crazy and moving all around, there would be no coupling, right? So you remove the coupling. You understand the reason why this whole concept was developed. Right? So by using all of it, you can easily design your own experiment. And I think by the end of this experiment course, you should be able to have some understanding of designing NMR experiments. Okay. Okay, this is very exciting. For a machine which gives you proton NMR in 100 megahertz, you know, a machine, a magnet which gives you a proton NMR in the field of 100 megahertz, these nuclei, all of them, have different frequencies. You know, you can pick and choose. I'll tell you, I want to detect boron. Which frequency I need to have for pulse? Boron. Boron 11. How much? Excellent. Okay, I would like to detect only phosphorus in my sample. Which frequency I would select for my pulse? I would like to have platinum. I just want to detect platinum in my sample. I want to detect only lithium. I want to detect oxygen 17. It's so easy, right? You just select, and let me ask you a question. Why they are different? Magnet is same. That's a good thing. You become ulama, sheikh, scholars. Now I want to ask you, I want to detect carbon 13 and proton together. That is a difficult question. What I would do? I want to detect proton and carbon, not together, but in one experiment. Okay, there is no detected design which can detect two things together. So I want to detect, if you answer this question, you get 100 rupees from Hina. Okay, I don't have any. Okay, carbon 13, I want to detect carbon 13 and proton, my little beautiful proton, my little brother, and carbon 13, my stepsister. I want to detect them together. Design experiment for me based on your understanding of pulse and your understanding of bringing them on XY plane, because your detector is on XY plane. If anything is not on XY plane, you don't detect. You cannot detect. The simplest possible explanation of an experiment in which you wish to detect proton and carbon, not together, but in one experiment. On the stage of XY plane, which is called transverse plane, you have your little detector waiting for these magnetization to come in front of it and get the FID. Give me an experiment in which I should be able to detect them, carbon-13, one after the other, but one experiment. Yes, sir.
I think you set your pulse, the frequency, since carbon-13 the compensated frequency is around 25 megahertz, and proton is around 101 megahertz. You set your frequency between these two ranges, 25 to 101, so that by the time it gets to 25, it peaks carbon-13. Carbon-13 absorbs and gets 101.
Okay, nothing like this exists of having two different frequencies, because if you have anything between 25 to 100, somewhere in between about 67, you would be detecting something else. Right? Okay, so good guess. But that makes absolute sense what he's trying to say. You know, you can have as many radio frequency oscillators as you wish. Problem is detector. You can detect only one signal at time.
I think we can apply 100 megahertz and 25 as acceleration, but the FID would be different because of the difference between data and.
No, the detector can detect only one. Yeah, this is 2D, this is two-dimensional, but your mental gymnastics. You know, I can give you a very simple answer. I don't know anything like this exists, but what I would do, I would first bring proton NMR on XY plane. I will detect. Then I will give a 180 pulse to proton NMR, bring it to -z. At that stage, I turn on the radio frequency oscillator at about 25, and I bring C13 on XY plane. I detect C13. My experiment and finish. Alas, I was able to play with them based on two things: frequency and the angles. Where you would like to that anything which is not an XY plane is not detectable. If proton is not an XY plane, you cannot detect it. If C13 is standing there and you bring only proton on XY plane, you only detect proton. You remove proton, you take it back to -0, wherever you want to, and then you bring C13, you detect C13. And in one experiment, you are able to detect proton and carbon. Understood? That is how these multi-dimensional NMRs are experimented. NMR experiment, now on one axis you have C13, on the other axis you have proton in representation. So you understood that the utility of this, I mean, you would think that it is a useless exercise to bring that on XY plane. Now you should really develop some kind of an appreciation that it is by purpose. It is by design that you would like to play with this different elements. Let me ask you a question. Okay, I have this little OH in my ethanol. Okay, and this gives me a broad peak of proton. OH proton. And OH proton is unfortunately not at one place because it depends on the pH of a solution. You know, there's a lot of exchangeable issues and all that. I don't want to see that. I don't want to see proton of OH in my NMR experiment. We generally don't see that. What I would do, play with the pulse and let me know.
Go down at 180.
Wonderful. Select that particular frequency, which is only for proton. Give a 180 pulse and bring proton of OH down there. It no more exist. For the system, it's gone. And you don't see anything. You don't see any, it's called decoupling. You know the word decoupling? This is decoupling. C13, when you record C13, all C13 have, protonated C13 except quaternary C13. All C13s are coupled with protons because protons are nearly 99%. Right? Protons, all protons, all C13 have protons, CH3, CH2, CHs and all that. And C13 will be splitted. And C13 spectrum would be jungles of peak, extremely complex. Very, very difficult for you to understand C13. For instance, a methyl will appear as a quartet. CH2 will appear as a triplet. CH will appear as a doublet. And if you have 16 carbon, you would have hundreds of peaks. You cannot interpret that. So you want a decoupled C13 NMR spectrum. I want completely proton decoupled C13 NMR spectrum. Design an experiment for me. Design an experiment for me in which I should not be able to see any coupling with attached protons. Only C13 as a singlet. One C13, one singlet. How would I get rid of these protons?
Find the couple of
Absolutely. How would you decouple it?
give it 180 degree of pulse. 180.
180 or just turn on the radio frequency oscillation on proton, and proton is constantly oscillating. Right? It is like a fan. When you see a fan, you can see the roof. See, there are three wings, but if fan is running fast, it's just completely transparent. You can see the roof. Right? Isn't it? Similarly, when you turn on radio frequency pulse on the frequency of proton, turn on and don't turn off. In the entire duration of experiment, you have a broadband frequency given to proton, and all protons are constantly oscillating. They are not on XY plane. And then you play with another radio frequency oscillator with C13 and bring them to XY plane. The C13 will not see proton. Right? So it's a completely decoupled experiment. Now, the objective of all these experiments, which we will discuss in greater detail till then, the objective of telling these experiments to you is to give you an appreciation of the fact that why such thing is required. Why on the face of the earth I'm trying to make your life so difficult. Life is already too difficult, isn't it? Yes, Arjun? You're smiling too much. Amina. So I'll tell you that people in Sudan are wonderful, very intelligent people, but they are the most relaxed people in the world. Oh, it's Sudani here. There's one Sudani. So, because I traveled so many countries in the world, okay, so I reached Khartoum, 3 o'clock in the morning. There were so many people there at the airport to receive me, and they brought me to a hotel called Rotana. So it was like 4:30 in the morning, and I was worried because I didn't really sleep the whole night. I said, "What time will you pick me up for the conference?" I was the chief guest in a conference in Khartoum, in China Convention Center. She knows about it. Okay, and they say you sleep, and they literally answer my question. And I said, at what time you're going to pick me up in the morning for the conference? And my brother Jalal said, you sleep, please. Yes. I said, Brother Jalal, I'm asking you at what time you to pick me up? And at what time the conference will start? He said, conference will start when you wake up. So that was the best conference I ever had. Amna, is it right? But this is, I'm telling you. So I had many experiences. I was in every country except Cameroon, I think, but so many countries in Africa. Okay, so so 90 experts here, 180 down, but you can also have pulses somewhere in between, 45 pulses. You can have, there's so many pulses which you can play. And you can not only play with pulses, but you can also play with the frequency of which element you wish to detect. And in modern NMR spectroscopy, sometimes we are playing with several elements together. For instance, this experiment of proton broadband decoupled C13 NMR spectrum, we are playing with 2 elements, proton and carbon 13 together. And that is only possible in NMR spectroscopy. There is absolutely no other technique where you can distinguish between UV, you cannot distinguish between C30 or IR or X-ray or anything like this. This is only this technique which gives you this tremendous flexibility and selectivity that you can play with these elements. And this is the reason there are thousands of NMR experiments. Photon carbon coupling, photon nitrogen coupling, nitrogen carbon couplings, and others. Okay, so and I told you about spin relaxation that they relax, but this is a non-radiative relaxation. Generally, the energy which goes on into the system is dissipate into the environment with other solvent molecules and others, and then it goes back. It's called thermal equilibrium. You probably have classes, right? Some of you have class.
No, sir, this class took 2 hours.
Okay. What 90 experts will do to the population difference? Now, there's a tricky question. The population difference, where the population difference is gone. Now, there is no population difference between upper and down. The population difference is on XY plane. Okay. Then explain what will happen to the population difference when the 180 pulse is given. It goes to the higher energy state. What will happen if the radio frequency pulse is applied for unusually long time? Right? So you'll not be able to see any signal. You'll not be able to see any signal because nothing exists on X-ray plane. You can only see magnetization which is on X-ray because your detector is there. What are the factors which define population difference? Magnetic field, paramagnetic ratio, and natural limits. These are the free induction decay. Why we call free induction decay? Just explain. Decay pattern, like a beat. You know, if you have a musical instrument, or even that physics group में क्या होता था जिसको you mark है? हाँ? नहीं
Turning point.
क्या कहते हैं?
Turning point. Turning point.
Whatever. You put it like this, you see a beat, right? Similarly, if you have string on your guitar, then you see like this decaying pattern. So this is called decaying pattern. Free because there is no radio frequency to apply to them. I want to leave you with a bit difficult concept. And you see, when you give a radio frequency pulse, these M0 has to, you know, there are now two forces. One is magnetic field. The other is V1, right? Two magnetic fields are now, one is B0 and the other is radio frequency magnetic field. And when B0, B1 is applied, torque takes place. As soon as you turn off B1, the magnetization vector starts processing around B0 again and goes back. This is called, in physics, this is called mutation. When a system has to compromise between two applied forces, it's called mutation. Okay? Called mutational frequency because B1 and B0. B1 is always present. B1 is given and stopped. Right? So it has to compromise torque, turning, an angle. You can define the angle. You can define the angle and you can select the element. It's called mutation. These are some terminologies which I want to tell you. And then from the next point onward, we will start discussing, yes, mutation, N-U-T-A-T-I-O-N. Of course, this is a rotation, but this is, in physics, it's called mutation because two forces are interplaying. On magnetic M0, there is one B0, which is making it precise around or against the direction. But then you have B1, and that B1 will also try to do that, right? But this B1, you're not really applying it forever. You're applying it for a certain duration, and as soon as you turn it off, only one remains, and that B0. And that B0 again, they start processing around B0. And they process and they go back to thermal equilibrium. And this, during this process, it's called free induction decay. This is how the NMR is recorded. Now, all of them have to be converted. Frequency, this is a free induction decay. You see a decaying pattern. This is a time domain because half-life. This is the head, and this is tail. Free induction decay pattern, FID, has a head and a tail. Which one is more important? Head or tail? Both are important. You cannot really have, isn't it? But where is more information? Where is more information?
Fine.
No. Information about the signal. Because this has to be converted in frequency. Okay? And this pattern has information about nuclei. Where is the information content? More information content. Everything which is there, your frequency signal is only the transformation of this signal into frequency, time signal into frequency, right? So pre-induction decay, we do a lot of mathematics on it. It's called equitization. Sometimes, for instance, if I'm an NMR spectrometer, not meter, spectroscopist, then I want to save time. I don't want to wait until this tail appears because that takes so much time. I'm just looking into tail several seconds. So I say, okay, truncate. I stop here. I generate the tail by mathematics. I said, okay, I don't want that. I will generate the tail by simulation, by mathematical process, equitization. Also, I say, okay, signal intensity here, for me, it is more important. Okay. So I want more weight given to this part and less weight given to this part. What I will do? Remember, this is an analog signal. You know analog? Line. Can you do any mathematics on line? No. It has to be converted into digital. So analog to digital conversion. All lines need to be converted into numbers. Only you can do mathematics on them. Okay. So forget it when I say more. It's called ADC, analog to digital conversion. These lines are converted into numbers, and that numbers are then go to Fourier transformation, and you get between lines.
To convert to equations.
Hmm?
Convert to equations more than.
Yeah. So, if I would have to give more weight to this, I will multiply these numbers with some factors.
Yeah.
And if I want to give less weight to this, I divide these numbers with some factor. So you can play with FID. It's called equitization. You can, I often give the example. What is the best time in your day? Everyone has a best time. What is the best time for you? When you think you're intellectually bright, you are the best performer, you are the brightest at that point of time, you're the happiest man on the face of the earth. Tell me.
In the morning.
At what time?
Yeah.
So if I'm your boss, I'll give you the most demanding work at 10 a.m. What is the worst time? After Fajr. Is the worst time? Worst time. Bad time.
This time.
Worst bad time.
What time? And after lunch.
After lunch. You're feeling sleepy. I will never give you any assignment which requires brain work. Exactly. So similarly, these FIDs are given weight where the information is more important, you multiply. Where you think information is least important, you divide. Okay, so there's a lot of computing carried out. Now, by the way, in the world of corporate world, they have psychologists and psychiatrists for every individual. And they identify the best time during the day and the worst time in which they're not performing. They cannot perform well despite their best effort. And these corporate firms identify that best time and give them the most intellectual demanding time at that. Okay. So is this a human psyche? You know what is the best time for me? When I'm here. Thank you. Thank you very much. Okay, I'm traveling tonight to. Okay, I'm traveling tonight to Brazil, and I will be in Brazil for a few days. So next Saturday might be relaxed. Because I will be traveling from on Saturday about 15,000 kilometers. So inshallah. Okay, so Islam, Jazakallah khair.
Students, we are going to discuss the quiz. So anyone who's interested can stay, and those who are not interested can leave. We are going to discuss the quiz that we have given to you on Wednesday. I'm going to discuss that. If anyone is interested, can sit, and if you see that if you want, you can leave. So we have discussed the first question. Now I'm going to discuss the. Yeah. Okay. The second question. For the second question, the correct answer is B. So how many of you marked B? What about others? They didn't know? So who is going to explain that why the option B is correct? Who is going to explain? Or you want me to explain? Please say something. Okay. Okay. Whenever you have to decide that is it a dipolar nuclei or quadrupolar nuclei, you need to basically know the energy state. And for that, you need to know the formula to calculate the energy state. And for that, which is 2I plus 12. So I have given you a spin quantum number that is half. So if you multiply this by 2 and then plus it with 1, you will get answer 2. And any nuclei which has energy state that is 2, that nuclei is dipolar. So any nuclei which has a spin quantum number greater than half, it will be quadrupolar. Okay. So correct answer is B. For the question number 3, I think it's the most easiest. The correct answer is D. It is not the part of your spectrometer. Okay. I think I don't need to explain this. And then the question number 4. Based on the gyromagnetic ratio of the C13, you need to identify that if you are recording your experiment on 800 megahertz, what will be the radio frequency for your carbon? So how many of you marked C? I think most of you have answered it right. And sir has explained it in today's lecture as well. Based on the gyromagnetic ratio, the gyromagnetic ratio of carbon is 4 times lesser than that of your proton and proton Lamer frequency. So whatever the Lamer frequency or the frequency of your NMR spectrometer, the frequency of your carbon will be 4 times less than that of your proton. If you are recording it in the on the spectrometer of 200, what will be the radio frequency for your carbon? 50. You just need to divide your Lamer frequency of your spectrometer by 4. Okay. So now the question number 5, which is that you need to distinguish the continuous wave from your pulse NMR. So correct answer is A. So how many of you marked A? And how many of you didn't mark it? You marked B. Why? The correct answer is A. Why? Because if you remember, sir has told us that in continuous wave, you basically give a sweeping of radio frequency whenever it matches with the absorption frequency of your particular nuclei, it will absorb and it will give you a signal. And in pulse, you give basically a short burst of radio frequencies which will excite all the protons which are present in that particular molecule. Okay. The B is wrong because continuous wave NMR also give you a frequency domain spectrum. It doesn't give you a time domain spectrum. The C is wrong because continuous wave is not faster. It is more slower than that of your pulse field NMR. And D is also wrong because pulse NMR is widely used for you are doing the multi-dimensional experiment, and that is also the case that right now in modern NMR spectroscopy, we are not doing anything with the continuous wave NMR. We are right now doing pulse NMR. Okay, so I think I'm done with the quiz. Do you have any question? Question number 5. Okay, question number 5 says that which of these statements distinguish the continuous wave from the pulse NMR? Do you know about the continuous wave NMR and the pulse NMR? Do you know this difference? Please say something. You know what is the continuous wave and what is pulse NMR? First you tell me, then I will explain this question. Whatever you know, whatever you do. First let me clear this to him. Whatever you know about continuous wave, explain that to me, then I will answer you. Please stand up, come here. शर्मिंदा होने की, परेशान होने की कोई जरूरत नहीं, आ जाए, आप सीखने के लिए आए हैं, आ जाए. You don't know? Okay. In continuous wave NMR, which is the old version of NMR experiment system, we actually give radio frequency very shortly, or like first we give 200, then 201, then 203, and then 204. Wherever the frequency of that matches with the absorption energy of your proton, it will absorb that radio frequency and it will give you a signal. Okay, you have to sweep the radio frequency from one value to another value, and when whatever protons are present, they will come slowly if they absorb that particular energy. In pulse NMR, what you do is that you give a short burst of radio frequency which will likely contain the energy, or you can say the radio frequency that is needed to excite all kind of protons which are present in that molecule. you excite them at all at the same time. But in continuous wave, you don't excite them at all at the same time. Okay. So what does it mean? That you are creating, you are having the signal one after the other. But in pulse NMR, you excite them at all, you excite all the proton at one time, and then allow them to relax, and then you will record your signal. Okay, this is the difference between the continuous wave and the pulse NMR. Based on that, you can say that your statement A is right. B is wrong. Why? The continuous wave also give you information in the frequency domain. Okay, not in the time domain. Option number C is wrong because continuous wave is time taking. It's not faster. Pulse NMR is faster than that of your continuous wave. D is wrong because your pulse NMR can be used for designing the multi-dimensional experiment. Okay, while right now we are not using the continuous wave NMR anymore. Is it clear to you now? Okay, now you can ask what you want to
No,
ask.
just,
You want to explain this? Jim?
when you talk with him, I thought you want to ask us.
Okay. So I think I'm done. We can end our class here. Okay, thank you. Firstly, I would answer.